try to compare the electron migration and the thermal migration. As long as you there's a electron migration or thermal migration happen in your systems, we need to modify the driving force acting on these diffusing atoms. For electron migration, we need to end the beta, and the thermal migration, we need to end the heat of transport. And we'll also show you how to determine the beta and heat of transport in your mature systems by yourself. Okay, then as long as you modify the driving force, so you know the atomic flux also need to modify, and only the change one is the driving force part. Okay, so we have some remark here. The effective charge of diffusing atoms for electron migration somehow can be considered. The idea is similar to that we talk about the heat of transport for thermal migration, okay? Because and don't forget the sign and the value is meaningful to describe this direction of the moving diffusing atoms, okay? So before we ended the thermal migration part, we are going to give you an example we call the vacancy-mediated thermal migration. And the material system actually we deal with is the vacancy-mediated materials. Just a remind, when we talk about the diffusion, atomic diffusion, actually there are like 4 or 5 different types of diffusion mechanism. And one of that is we call a vacancy-mediated diffusion mechanism. And this one, the detail will be introduced in chapter 4. But I'm going to just give you a quick review for this one. What's the vacancy-mediated diffusion mechanism? Is the diffusing atom at a substitutional site or lattice point will exchange with a neighboring vacancy through atomic jumping. So this is the only way to allow these atoms diffuse through these materials. So based on this idea, you know the diffusivity was determined by 2 major factors. The first one is we call the concentration of vacancy in these materials, which will proportion to the vacancy formation exponential minus vacancy formation energy divided by kT, right? And as you know, well know, the vacancy formation energy in different types of material will be different. And also, you know, based on this equation, you know, when you increase the temperature, then the concentration of vacancy will increase in the meantime. So the first one will be the vacancy concentration, and the second one will be the atomic migration energy, which will be, some people will call it as a mobility, will proportion with the exponential minus migration energy divided by kT, migration energy of these substitutional atoms. So in order to complete this diffusion in this kind of materials, so the total energy which allow this atom to be overcome, included the vacancy formation energy and the vacancy migration energy will be considered as energy barrier or activation energy of this diffusion mechanism. So now you have this idea, right? So let's move back. So this material actually is a pure material, and the diffusion mechanism is mainly react on the vacancy-mediated diffusion mechanism. Under this situation, it implying that the vacancy concentration cannot be ignored. And as you know, we apply a temperature gradient on these materials. And in order to create in order to have a thermal migration phenomena, as you expected, the temperature gradient here is definitely for sure is very high. And some people ask about how high may probably induce thermal migration. I can give you some the scale. For example, like the 10 degrees C per 100 micrometer, roughly, but slightly depending on different materials. Okay, so under this situation, when I apply a temperature gradient on this vacancy mediated materials, as you know, the concentration of vacancy cannot be ignored. So when you apply the temperature gradient on this type of material, there are two parameters you need to consider, which will affect the atomic flux. The first one is the intrinsic vacancy. Is due to the vacancy concentration will vary with the temperature, right? So under this situation, as long as you apply a temperature gradient on these materials, you can observe they're definitely accompanied with the vacancy concentration variation along your materials. So due to this variation, that will induce a vacancy flux. It means that also there's an atomic flux, right? And the second stuff is the one you learned from previous slides. This material will have a thermal migration. So these two factors will affect the atomic flux, right? So first of all, we consider the first one is due to the vacancy variation, the concentration vacancy is dependent on the temperature. So as you know, the equilibrium vacancy concentration will proportion to exponential minus vacancy formation energy divided by T. Vacancy formation energy will, depending on different material systems, will have different value for this one, but the order should be like 1 or 2 eV for vacancy formation energy. And as you based on this equation, you know when you increase the temperature, you can observe more vacancy be created. So as you know, based on these figures, we apply the temperature gradient on this one. So we will also have a higher vacancy concentration at higher temperature and lower vacancy concentration at lower temperature. This concentration variation will lead the vacancy flux toward to the right-handed side, right? And this also means what the atomic flux will be go to the opposite direction, to the left-handed side, right? So this will be the atomic flux due to what? Due to the intrinsic vacancies exist in these materials. Okay. And don't forget, this atomic flux is one factor, right? And the one you also need to consider will be the thermal migration happening in these materials. So so what's the effect of thermal migration on the atomic flux? The one you probably will write down, the atomic flux will be equals to mobility, concentration, and the driving force, right? Please so far just ignore this term. If we just consider the thermal migration acting on materials, probably you will write down the atomic flux express the mobility, concentration, and the driving force, right? But now in these systems, you cannot ignore, it's a vacancy mediated one, you cannot ignore the intrinsic vacancy concentrations, right? So based on this, you know in this case, you need to end it the extra term to modify this atomic flux, right? So here, after serious experiments performed by this professor's team and founded in 1964. After simulation and also experimental results, they find if the material you're dealing with is vacancy mediated one, you need to modify the atomic flux by ending this vacancy gradient effect here. So use the heat of transport minus the vacancy formation energy. So some people probably will ask, Professor, is this true? But this result actually is be confirmed by the simulation and also the experiments. So you can the detail can be checked by in this literature. But what I'm interested in would be yes, you minus vacancy formation energy effect or vacancy formation energy turn here, but I'm just curious, is this meaningful or is this correct and can be applied on the material no matter is with the positive heat of transport or negative of heat of transport one. So I'm going to discuss these cases step by step. If we have the heat of transport, small is a negative heat of transport, which means what? Which means the atoms, due to the temperature gradient, the atoms be pushed toward where? Toward to the from the low temperature toward to high temperature would be go these directions, right? So due to the Tm, we can have atomic flux to move to the high temperature. So the direction will be the left-handed side. Under this situation, we also know there's atomic flux due to the vacancy concentration variation, right? So this plus this. This one is minus, or negative. Minus a positive one is more negative, right? So the flux will increase. It's reasonable, right? This plus this one, you got a larger atomic flux toward to left-handed side. But however, but on the contrary, on the other hand, if the heat of transport of this diffusing, this in substitution of atoms is positive, which means what? Which means the atoms be pushed from the high temperature toward to low temperature, so the atomic flux will be go to the right-handed side. But if the materials we choose is vacancy mediated one, so it will have this kind of flux toward to upside direction. So this one minus this one should be, we got a smaller atomic flux toward to right-handed side, right? Let's check this equation. If this one is positive, you minus a positive, so you get a smaller atomic flux toward the right-handed side. So everything turns out this equation is reasonable no matter the materials with a positive or negative heat of transport, right? So based on this case, you need to remember no matter is in when you apply whether there's a EM or TM exists in your materials, different materials you should have different considerations or boundary conditions. You need to think about that. Okay. So I'm going to give you a quick summary for the TM thermal migration. If let's exist a thermal migration, we need to modify the atomic flux by what? Depending on what types of material we discuss. If it is a dope materials, and that means the dopant at the interstitial side. So when you apply a temperature gradient on it, the atomic flux of these interstitials can be separated into two parts. The first one is due to the concentration variation of these interstitials, and the second one will be due to the temperature gradient, so can be expressed like a mobility, concentration, and the driving force. If the material system we discuss is a vacancy mediated materials one, so based on this, atomic flux should be modified by this vacancy formation energy part. And this also can be used no matter the material with a positive or negative heat of transport. So give you a quick summary here. What's the thermal migration? It's a cross effect between the diffusing atoms and the heat flow. We can characterize and describe this phenomena by heat of transport, and this property, heat of transport, actually is related to material properties, right? every material have its own heat of transport, especially even if the material system is different. For example, like we have the tin, we have the lead and tin alloy, and the copper and tin alloy. Even when we talk about the tin, but in different material system, the heat of transport may be different. So let's say for different material systems, you need to measure the effective heat of transport individually. Okay, so this idea is very important. And the sign of heat of transport determine the direction of the atomic flux driven induced by this Tm with respect to temperature gradient. Okay, so I just highlight some important equations. Hope you can. This one is especially to describe what's the heat flow, what's the relationship between the heat flow when you observe the diffusion at the constant temperature. We still observe the heat flow due to what contribute from the atomic flux, right? And also the interaction between the heat flow and atomic flux. And this term is due to the this is atomic flux driven by Tm. Okay. So next, we also give you some examples really happen in semiconductor industry. So in more like the case studies, because some people usually the heat of transport, the thermal migration is very important in the solder bond. Especially people focus on lead-free solder bond, fabricate a lead-free solder bond. But no matter what type of solder bond they want to investigate, the very important part is to determine not only determine the heat of transport of specific material. Usually people, because this usually used in solder bond is in microchips, right? So people want to directly measure the heat of transport on or in the solder bond directly, not only on the thin film, right? So it's different. For example, like if you want to measure the if you fabricate this kind of composition of materials, then you measure the heat of transport. Sometimes somehow it's probably the phenomena may not be the same with what you observe this material made into the solder bond. So the question here is how we measure the heat of transport of the solder bond, in our device. So here, in the beginning of this sections, actually we already show you if your application of your materials is directly point out, is focused on the solder bond, we would suggest you to additional met to solder bond nearby the solder bond which you are interested in, but without the current passing through. So they can share the temperature gradient. Then by analyzing this two solder bond, you can have an idea and confirm whether the thermal migration did happen in your solder bond. By what? By checking the SEM images before and after you applying the circuit. Then you can know whether the composition of this solder bond changes after when there's an exist of temperature gradient. Then you can know whether the thermal migration did exist in your solder bond. Then, so based on these figures, I believe you can determine the heat of transport of specific compound, right? Because, for example, we observe the tin moves toward to high temperature. So based on this case, we know the heat of transport of tin is negative. Okay, so you can check here, but don't forget the solder bond, really the role of the solder bond in the semiconductor chips actually was suffering two driving forces. The first one is the electrons flow. The second one would be the temperature gradient generated by this electrons flow. So there are two possible driving forces, right? Really coexist on the solder bond. So as long as you confirm whether there's a thermal migration happen on your solder bond, then the second step will be moved to here. As long as there's no thermal migration happen, if there's no thermal migration happen, then you can understand that then now the solder bond only suffer the electrons flow. So next you need to determine whether EM happens on your solder bond. So this is the whole story. We just for this one we consider one factors, right? Consider whether TM happen. Then we also take the cross section of this solder bond and analyze the composition, something like that, and void formation, extrusion, something like that, and we can identify the EM effect. But if did exist thermal migration, then the solder bond in your chips actually they suffer the TM and EM in the meantime, right? So this is because it suffer the TM EM together, so it will turn out the things more complicated. Okay, so let's give you the example here. The question here actually is we have a solder bond to bond the silicon substrate and the copper substrate, and this solder bond actually is there's a current passing through, and also due to this current passing through, it will generate a temperature gradient co-applying on this solder bond. So my question here would be, in this kind of structures, can you directly determine the sign of heat of transport in this solder bond? Can we directly determine that on this type of structures? So the material is pure tin, and after 6 hours, we apply the current density in this order, and after 16 hours, then they take this SEM pictures, and in this case, they find that there's a large void form near the silicon die when they apply the electrons flow along these directions. And next, they try to switch the directions toward to up the switch directions. But after 6 hours, they observe the voids get smaller, so only observe smaller void form near the silicon substrate side. So based on this type of design, they just simply switch the direction of electrons flow. They successfully to estimate the sign of heat of transport. Why? You can expect this is electron flow, right? So the atomic flux definitely go this way in these directions, and will go this way in these directions, right? But this solder bond also suffer the temperature gradient. So that's the other atomic flux driven by temperature gradient, right? But the temperature gradient always is higher, this is lower, so I'm sure the atomic flux driven by temperature gradient is the same direction, right? For these two cases, right? Even though you switch the direction of electrons flow. So what's the directions? This one ended this one atomic flux will get larger, and this one ended this one, the other atomic flux will go smaller. So you can guess, right? If the atomic flux is go this way, this plus this will get larger, this plus this will get smaller. It seems okay, right? But if you assume the atomic flux driven by temperature gradients go upward, this one should be smaller. This one should be get more smaller, right? But the result is not that, right? So we can confirm the atomic flux driven by temperature gradient or Tm is go this way. So for the tin, you can see that the heat of transport is positive because move the atoms toward to low temperature. So this is how we can directly estimate the sign of heat of transport in the solder bond in your micro device directly. And that's the other concept I want to remind you. This idea is very interesting because in most of cases, as long as the line width of the interconnector dramatically decrease to several nanometers in semiconductors, as you expected, the current density dramatically increased, right? And under the situation, that definitely increase or induce the Tm or Em and Tm together. So it turns out we cannot avoid them. So the newest I designed for the solder bond here in semiconductor industry will be turned out. How about if we can allow the atomic flux increase induced by En can directly counterbalance by the atomic flux induced by Tm, the same value but opposite directions, then it will be the most ideal solder bond, most ideal materials for solder, serving a solder bond, right? Because the net flux equals to 0, so we are not going to observe the void formation or extrusion on the solder bond or any composition change, right? So this is the new design idea for fabrication of solder bond here. Okay, so I'm going to give you a summary of the Em and Tm. Em actually is a close effect between the diffusing atoms and the electrons flow through the momentum exchange, and we can quantitatively characterize the effective charge of diffusing atoms, and also this value, the sign of the effective charge will tell us the moving directions of the diffusing atoms. Okay. And the Em also can be counterbalanced by the concentration gradient and the stress gradient. And we also give you some example here. But as long as the current density increase dramatically, the concentration and stress gradient cannot counterbalance them, then you can observe the extrusion and void formation in your materials. That's what we don't want to see, right? We want to avoid that, right? So that's the other interesting effect we call a thermal migration. Thermal migration actually is a close effect between the diffusing atoms and the heat flow. We also can quantitatively characterize them by heat of transport. And this heat of transport also can be counterbalanced by the concentration gradient, but the same idea. If the temperature gradient, like atomic flux driven by the temperature gradient is too high, the concentration gradient don't have chance to counterbalance them, then you can also observe the void formation and composition change in your materials that you don't want to see, or you don't want that happens in your materials, right? So the newest idea is, how about why don't we just design a material which has an atomic flux induced by Em will be the same with that induced by Tm, the same value but opposite directions, something like this. Then we don't need to additional think about how to avoid them, right? Because they usually or in most of cases, they will be driven unless exist of this atomic flux, right? Because it's very difficult to avoid them as long as we, especially when the light width of interconnector decrease to several nanometers in semiconductors, it turns out it's very difficult to avoid these two effects. So why don't we just allow them have the same value but upside direction to directly totally counterbalance each other. So to reach the net flux equals to 0. So this will be the new idea for designing materials, right, for solder bond.